All right, ladies and gentlemen, we're going to look at carbocation rearrangement. So I've already got a mechanism on the screen for you. And we're supposed to predict the product. And if that H takes its electrons and makes a bond there, it's called a hydrogen shift. As opposed to if a carbon moves with its electrons, the next one, back to a hydrogen shift for the third one. There's only two types of shift. And how far away every time is the shifting bond? How far away from the cation? Is it 2 carbons away? 3 atoms away? It's the next carbon over, huh? It's the next atom over. So you're allowed to move anything from an adjacent position. Okay? All right. I want to remind you that I think every one of our cations I picked, coincidental, is secondary to start with. Carbocation rearrangements only happen if they get more stable. And you guys read about substitution and carbocation stability, but I don't think you read that word too much, substitution. I think you were reading about degree signs all weekend. Tertiary carbocations have the most hyperconjugation, and secondary, they're in second, and primary, last place, has very little hyperconjugation. So you will not be rearranging to less stable carbocations. The driving force is creating a more stable carbocation. So our first one, we're going to definitely get a rearrangement like drawn here, because when you are finished, you're going to have this and this. If you're curious about the H that moved, here it is. You don't have to show it, but there it is. And now your cation is over here, which is now tertiary cation formed. Tertiary is more stable. So I guess predict the product, indicate whether, as we say yes, it will happen because the cation formed is more stable than the original, which was what category? Secondary. Now in this one, you take your ethyl and move it here, and your cation's there, which is still secondary. So here's the answer to your question. Red and blue. It erased my carbon shift, but it doesn't happen. No. Cation formed is not more stable. So you don't see that rearrangement. Okay. Next one looks promising, but I'm going to have to remind you about stuff that we didn't cover as much as we normally do in previous semesters. Okay, C+ is on cyclobutane. Do you agree? When you're finished, it's on one of the carbons of cyclobutane. Angles in cyclobutane. You guys remember this from grade school. What's the angles inside of a square? Say it again. 90 degrees. C plus is sp2. What's your ideal angle for sp2? 120. This causes angle strain. It's not a good thing. It's reason number one for no. Okay? It doesn't happen. It's not all about hyperconjugation is what I'm trying to say. There's other things. Also, here's cyclobutane. Small ring equals rigid. So you've got this right in front of this. And this right in front of this. This is called eclipsing. Same for down here. Yellow in front of yellow. And it's all the way around this ring, not just these 4 H's I drew. This happens when the rings are so rigid they can't sigma rotate. Like our chairs were fully free to sigma rotate. Remember that? Our chairs never had any of this eclipsing. And I skipped over this because I knew I wasn't going to have it on your first test. See, I can do that. But it's happening now. Eclipsing causes torsional strain. So keep in mind these 2 red things. These things are relevant for cyclobutane and cyclopropane both. Cyclobutane and cyclopropane only. Why? Small ring is rigid. All other rings are not as rigid, so we can get away from torsional strain by doing rotation. And angle strain. Well, the angles get bigger as your rings get bigger. So angle strain goes away too. So if you had to say in words why this rearrangement doesn't happen, you'll say because you're creating too much strain, ring strain and torsional strain. You should tell me you know about both. Okay? And we'll see an example maybe in our activity 4 where you have to make that explanation. I think it might be activity. It'll be on Wednesday. Activity 4 is a new mechanism that's not on your test. Okay? I think the story down below is not a no anymore. I want to be able to see everything. There we go. Yeah, we're going to get to a bigger ring. Now, if you're like me, and when I was first learning this, I couldn't see this stuff. I needed labels, and I needed to spend a little time with it. So I'm going to give you some labels, okay? In orange, A, B, C, D, and E. Same labels down here. So I'm breaking the bonds between B and A and making a new bond between B and E. How do you do the product? Copy everything except for the bond you're breaking, exactly how you see it. Do not try to revisualize anything. Copy everything except for BA. All right, so far mission accomplished, right? And it went A, B, C, D, E. And where's the new bond? Between B and E. Which atom lost a bond and didn't replace it? There's only one. Give me a letter. A is a carbocation. And you say, but wait, it's secondary. Why would this happen? Secondary, but has, I need the magic words. Less the two new strains. Give me both of them. Same out loud. Angle and torsional strain. This is my part of explanation for yes. That's more important than the fact that this thing has the same hyperconjugation. That explanation says yes. And I think that explanation says yes here and here. Okay? And down there, I'm going to do the same thing, except no bond between A and D. A and B still bonded, to C is bonded, to D. Still has a methyl, still has a ethyl up here. Put the labels down. A, B, C, and D. And what's E bonded to now? D. Once again, I believe it's the same letter that lost out on a fourth bond, isn't it? Yeah. Plus. And it's different than the one above it, right? Here, the plus charge above is between two methylated carbons. And the one here is next to a methylated carbon, but not one on the other side. So they're different. Cool, huh? Because you're getting rid of a lot of strains. Good stuff. We're doing really well on time.